problems that are too big to be solved?
So this is work that is combined with industry and university, and it's a very practical application, and I'll try to go quick. There's a lot of details here, so I'll try to go quickly on some of the things here. It's basically looking at electromagnetic inverse problems, and I will basically talk in the beginning about the forward problem, because it's an integral part of how we solve the inverse problem. I'll say a few things about it in a second. And then I'll say why there are some of these problems are called too large to be solved. We're talking basically about problems that are on very, very large domains with lots of details. So there's a multi-scale structure to these kind of problems that you want to resolve very small features and very large features at the same time. And they require very large meshes in order to be able to solve them. And then we'll talk about techniques that allow us heuristic techniques that allow us actually to solve these things, because until recently people said this is not going to be solvable in any reasonable time. And the techniques we're going to talk about them is mesh decoupling and, well, multi-scale methods. I see I've made the German pronunciation for this, and stochastic programming, which is a very important feature in inverse problems that recently people have started looking at in inverse problem and machine learning. And I think it's worthwhile noticing what this thing can do for you for many of the problems we have. And then I'll have a bunch of examples, some synthetic, some realistic on real data. So this is a classical electromagnetic experiment where people put sources. In this particular case, I'm talking about a loop source. So people put currents in this loop, it's alternating current in this loop. Or they basically put current here, they shut up the current at one particular time, and then you measure some kind of a decay curve. And the data, you can measure it after a certain time. You can measure data, you put sensors over here, and then you measure data, let's say, that looks like this at a certain time after the shut off of the current. You can measure data in borehole, you can measure different things here. And again, the sources can mean frequency on time, receivers, and the system that we're going to be looking at is Maxwell's equations. So for those of you who don't remember, that's what we're looking at. It's equations that connects the electric fields to the magnetic fluxes. So here's my electric field, here's my magnetic fluxes. We're assuming we know the magnetic susceptibility, which is relatively constant in the Earth. There's small variations. And the conductivity, the electric conductivity, is the guy that is changing very, very quickly, relatively speaking. So just examples, if you have some rocks, which are called massive sulfides, would have conductivity of something like 10 to the power of 4, 10 to the power of 5 Siemens per meter, while the Earth around them will be 10 to the minus 3 Siemens per meter. So the contrast is going to be very, very large for these kind of problems. If you notice, I'm ignoring the displacement currents, basically the part that Otto was talking about yesterday, the epsilon d, because we're looking at the late time diffusive part of the equations. The goal is, again, to look at these equations and to get sigma. Now, to connect things to what we've seen maybe in the previous days here, in the static case, so if you assume that you have constant current all the time, and you don't shut off, you get back the DC resistivity equation. This, by the way, comes from the fact that in the steady state, this disappears, the curl is 0, so the electric field is the gradient of a potential function. Then you take the divergence of this equation, and you get back the DC resistivity equation. That's the one. So in geophysics, it's called DC resistivity. Here, everybody knows it's the Calderon problem. DC resistivity actually is a terminology that came way before Calderon problem. Schlumberger brothers actually started working with this technique in the early 1900s. So it's a very old technique. People are using it to detect minerals, to detect salt water. They're a geotechnical application. And there are very well commercial packages for this particular problem right now. So there's lots of literature and commercial packages to solve this particular thing, at least in geophysics. Well, in this case, you measure the gradient of the potential, basically the electric field. That's what people measure. No, outside, on the surface, on top of the Earth. That's the. So how do we obtain solutions for these kind of problems, at least in the world that I live in? We're discretizing the forward problem, and then we use either what we call regularized least squares, and if you're Bayesian, you would use a map estimate. These are the things that you would definitely use. Now, one of the things that we always care about, we always obtain feasible solutions, so we always care that our solution is feasible physically. So if I get a negative conductivity, this is something that nobody, if I'm going to talk to a geophysicist and show him a negative conductivity, they'll say to me, something is wrong in what you do, you'll have to come with something else. So these techniques that we're using allow us to always get something which is feasible. Sanity check is always, you need to actually compute the misfit, so you need to see that you fit the data, because that's, to be honest, the only thing that we have in the problem. Everything else, the equations, everything that we have is something that we invented somehow, and the data is something that people believe in, so you always want to see the misfit. You want to see that you actually did a reasonable job in fitting the data. So that's another sanity check. And of course, these methods that allow you to regularize inversion, they have built-in mechanism to put some kind of a priori information to the problem. And of course, different noise statistics, which is also very important in a real application. Noise is not always white in many cases. So these are the things. So I'm just going now to the techniques we're actually starting to talk about. And the first step we have to do is to discretize the system. So this is Maxwell's equation, and again, since there is a lot of topics here, I'm going quickly over this. If you think about it, you're eliminating the magnetic flux B. We stay with an equation for the electric field E, and when we discretize it, we discretize in space first and not in time. You get something which looks like this. This is basically the curl transpose curl. This is the curl, basically discretization of this particular guy here, and this guy here comes from the sigma. So the sigma is represented as e to the power of m because it changes on an exponential level. And we base this is like a mass matrix for those of you who've seen this. And there is a time derivative on the electric field here. And what we're doing to discretize this thing, because close to the source, things changing very, very quickly, far away from the source, things are changing slowly. We're using some kind of adaptive mesh to discretize it, and we're using this type of adaptive mesh. It's called an octree method, where you basically have mesh that locally can look like this, and the interfaces are always two. It gives you some flexibility. It's a bit more rigid than tetrahedrous, for example, but on the other hand, it gives you much more structured matrices that you can work with. Mesh adaptability here is very important, and actually designing the mesh is not easy. So you can say, how do I actually get my mesh? There is a priori estimates, and these are based on, the Green's function, so you can work with the Green's function. So the Green's function, only for, of course, very simplified solutions, so it gives you only a very rough estimate of it. Then there is post priori estimates that people work on, and that's solving the problem on one grid and then trying to work it out. As I'll show you in a second, the post priori estimates are very nice when you're dealing with small number of sources, but in reality, we find it actually impossible to work with post priori estimates, and we are sticking to a priori estimates, and we try to make them relatively conservative so they can work for us for most problems that we have. The next thing to do is to look at time discretization. This is a very stiff ODE in time. This is, you can think about it as a fancy heat equation if you want to think about it. The curl is a vector Laplacian in some fancy way. So it's a very stiff equation, and we're using a backward Euler method, which you can write in this form. But the interesting thing is that when you take it back and you write it for all space and time, because we will need this thing, it looks like this. This is basically solving for time number 1. And then you can, after you take the solution for time number 1, you substitute to get solution for time number 2 from here. And every time you have to invert this matrix A, which is basically this particular animal over here. And this matrix can be very large. It depends on the number of cells you have in space. So if your discretization is very large, that will become a very large matrix. So this is how we do the forward problem, basically. It's a shortcut for how we do the forward problem. If you have the forward problem, if you have a very few number of experiments, so NS is going to be small, then the question is what's going to be the computational complexity of this? And I'm going to use a coin that is basically called solving how many linear systems I'm solving. That will be the coin that I'm going to measure how complicated my problem is. So since for every source, I have to go zip through here. If I have number of time step is nt, I need to solve nt times this linear system, and then I need to multiply it by the number of sources. So it's nt times an s. That's going to be the cost of doing something like this. So again, these are big linear systems that come from the discretization of a PDE. And if you can, then you can use the direct method. So if you can factorize these systems, then suddenly, and your time steps are the same. So if you're trying to make your time steps the same for every system, then you can go ahead and you can do one factorization and go and solve all these systems with the same factorization. So we try to make them as possible to be the same time step. It's not always possible. Then you try to make them only few factorizations. There's a lot of tricks here, but the point is that if you can do factorization, then it's really beneficial, and you will see that this factorization can also be used when you compute the inverse solution. So this is also going to be very important. Okay, so this was a very quick review of the forward problem. Now I need to deal with the inverse problem in the standard way. And now the idea is that I get noisy measurements of the field on the surface of the Earth typically. So I make either E or B, by the way, either the surface or a bit above it. And I need to recover the low conductivity, and we all know it's ill-posed. We know we don't have enough data. We know the data is noisy. And again, we're going to use regularization and minimization. So what do I have? I have some operator Q that operates on the electric field in all space and time. So that basically projects me from the field everywhere to the field of where my measurement is. And I want to minimize some kind of a output least square here, where I basically assume here for simplicity that my variance or covariance is the identity, and a regularization, some regularization that I can choose in some way, where my E field is basically solving this very, very large space-time PDE, discretized PDE. If you basically assume that you solve the linear system, you can express E as E of M, and express it as an unconstrained optimization problem, compute the gradient over here, which involves the sensitivity matrix J. The sensitivity is the derivative of the electric field with respect to the low conductivity. And it has a structure that looks like this. It's a multiplication of three matrices. This matrix is sparse. I'm not going to, again, talk much about it right now, but again, it's too short of a talk. This matrix here is sparse, and of course, this one is solving my space-time problem. So if I'm thinking about this thing, the matrix J is dense and not pleasant because I invert that particular thing. If there was no inverse over here, everything would have been fine. So the important thing to remember that you don't need to ever compute your sensitivities. Computation of the sensitivities is something that we used to do 20 years ago. Today, modern software, nobody inverts sensitivities. All you do is you do sensitivity times a vector by applying the sparse matrix to a vector, and then you solve basically a forward problem, and then you multiply by Q. And to do the adjoint, you do it in the opposite direction, which is basically what this slide is supposed to tell you. That if you want to do the transpose, you can just go ahead, multiply by this transpose, solve the adjoint problem, which is, by the way, a backward time-stepping problem, because you see if I need to invert this system, I'm solving basically this block first, so I'm starting from the end to the beginning. This is where you're solving backward in time. And then you're multiplying by this matrix G. So you can think that every time you want to compute the function and the gradient, you need to compute one forward problem, one adjoint problem, so it's equivalent to two forward problem calculation. This is all standard stuff and well known, I guess. Okay, so if I'm starting to think about different algorithms that I have, if I'm using steepest descent or nonlinear conjugate gradient or limited memory BFGS, I need to compute only the gradient for each iteration. So it's one forward, one adjoint. That's what I have to do. If I have more than one source, I need to store all these fields because this matrix G that we just had a second ago here, sorry, the other way around, I guess. Where am I? This G involve the solution. So if I'm actually using method that require all space and time, I need to store the solution at some point, and this is going to be an issue, as we'll see in a second. And but I don't need to have basically dense linear algebra because the dense linear algebra is hidden inside. I don't have to solve any dense linear system. All the systems I'm solving are sparse, so that's nice. The problem with all these first-order methods is that the convergence method is too slow. So the next guy in the food chain is going to be the Gauss-Newton method, where you solve something like this. Now, for this, you're going to be solving with some kind of a conjugate gradient method. And each iteration of the conjugate gradient method here is going to be expensive. It will require one solve forward and one solve backward. And you need to store all the fields for all space and time for all the sources and receivers, which is going to be an issue in a second. So if I want to now kind of ask myself, what's going to be the cost of doing something like this? Well, again, my currency is going to be the number of linear systems I'm going to solve. And each gradient, I will have to do 2 times number of sources times number of times that I have to do. If I'm doing a Gauss-Newton method, then I would have the number of conjugate gradient iteration that I need to solve on top of this thing, and the number of Gauss-Newton iteration I have to do. So I'm looking at these things, and I'm asking myself what happens. And again, there is no exact theorem. You can say we all know it's linear convergent, and we can talk about asymptotic things. But in practice, and we see it many times, if you have something like 60 time steps, 2-3 sources, it takes you roughly 50 Gauss-Newton iteration, and you decide you're doing only very few, 5 PCG iterations per step. You're calculating how many linear systems you're solving, and you realize it's about 60,000 linear systems. And again, this is PDs, so it can take you hours to days on today's machines, and the memory requires storing the space-time history for all these things. So you say this is doable. In today's machines, this is doable. And this is more or less the state of the art for most codes that are out there. So I want to show you an example for problems that people say are more difficult. And this is a movie which was stolen from a company, a Norwegian company, that is looking at electromagnetic data that are collecting data from the air. And this is stuff that is flown right now all over the world. This is very common type of survey that is flying. So this is a loop. This is a person, as you can see from here. And this loop is being flown, as you can see in a second, by a helicopter. And basically, as it flies, it measures almost every 10 meters. It produces a signal, and then measure the reflection, not the reflection, but the decay, and goes again and again and again. So you can see that this is the type of arrangement that you have over there. Interesting things to notice, kind of just for that we all like to think that cows are spherical and the Earth is flat, but in this case, you can clearly see the Earth is not flat. Well, we don't have cows in this thing, but I promise you they're not spherical. So we have to address the fact that if we're going to solve these kind of problems, you really have to consider solving realistic problem where things are not necessarily flat and simple. Okay? But this is the type of problems we want to solve. So I'm going basically back to the same calculation I've done, and now I say, if you look at the number of sources here, because it flies on a very, very large area, it's going to be about 1 million sources, if not more. For example, right now, the government of British Columbia have done and doing more survey like this when they cover most of British Columbia. So there is a huge coverage of this particular thing. The resolution that people say they want out of this is 10 meters. I'm not sure I believe them, but that's what they say they want out of this. I mean, if it's not 10, it's be 25, 30, 50 meters. And it's going to be flying over 200 kilometers. So you can imagine how large this thing is. You have very non-trivial topography for these things. There is going to be non-trivial geology. There are going to be oceans. There are going to be lakes. All these things have to be taken into consideration in your modeling and in your inversion. Okay. So when you start doing the same, and it's the same slide, the only thing I change here is the number of sources, really. And you get back to the point that you have to do something as 10 to the 10 linear solvers. And in that case, you scratch your head and you say, probably I'm not going to be able to do it. And until recently, and recently I mean more or less last year or a year and a half ago, people consider these kind of problems as non-doable. And the only software that was existing for these problems is basically assuming that the Earth is a 1D Earth. And then the only thing that since the Earth is 1D, every place is independent. The PD is reduces to an OD. And you can say, here I'm going to do, I pretend it's 1D. I pretend here it's 1D. I pretend here it's 1D. And then you can do it very quickly. But of course, you're missing the whole 3D information that you have in the content. So this was until more or less last year, the state of the art in this particular field. And again, we looked at this problem. We started actually about 2-3 years ago to look at this particular problem, and we thought we can do better. And we thought that it's not one thing that will improve the situation, but there's a number of things that you can combine here to really get things under control. So one thing, it's clear that if the linear systems you're inverting are very large, well, you're in trouble. So inverting a very large linear system, and you have so many of them, there is no way you're going to be doing it. So one thing you want to do is you want to reduce the size of the linear systems. That's an obvious thing. So this is being done by mesh decoupling, as we're going to show you, and multi-scale methods. So these are two things that are important here. The next thing you want to do is you want to reduce the number of linear systems, because you can claim, and probably justly so, that geological targets are bigger than 10 meters, typically. So if you're collecting data every 10 meters, you're probably oversampling. So to do something with the fact you're oversampling, and to get something a bit nicer, and this is where stochastic programming exists right now. There is a lot of work on stochastic programming that allow you to use problems that are overly sampled in order to generate some efficient algorithms around it. And I think this is actually, from my point of view, this idea of stochastic programming, the idea that you can turn out a deterministic problem into a stochastic one and actually get more efficient algorithms than you would think if you have a deterministic problem. To me, it is a revolution, personally. I mean, if you talked to me 4 years ago, I would say, no way you can use stochastic methods to do better than deterministic ones. I changed my mind after looking at a few things. The last thing is, which we're still working on, is parallel computing, and in particular, something which is called asynchronous methods. So when you're solving problems on many, many computers, you can think that information doesn't arrive at the same time. And if information doesn't arrive at the same time, you will have to deal with this, because a lot of these methods assume that you get all the information at the same time. How do you deal with information that not arrive to you at the same time? So you have to modify your algorithms. So here's the first idea. The first idea is mesh coupling, which is a really trivial idea in some way, but it actually becomes a bit more complicated as you start going. So let's say that the sources are covering this particular area. So you fly your helicopter like this, because that's actually what they do. They cover, they go back and forth and back and forth. And you have a source. Every blue point here represents a source. So you can come and say, when I'm actually looking at the solution of problems that the source is here, why do I need to have fine mesh? What do I need to solve with this mesh? This is the mesh for the whole inverse problem, but I decouple the mesh of the inverse problem from the forward problem, and I'm going to be solving, for example, on this mesh, sources that are around here, and then I'm going to move the mesh with me. So I'm going to generate many, many different matrices for each location. I'm going to have its own matrix, which represents the forward problem for that particular area, and I'm going to be solving different matrices for different problems, and of course I can do them in trivially parallel way. And because of that, the mesh is actually going to be relatively very small for each particular source. So this looks like a simple enough idea, and to be honest, if your Earth is flat and everything is okay, that's really a simple idea. I'm not going to actually discuss this much. This is more or less what the mesh looks like if the Earth is flat. But there is a complication. If the Earth is not flat, then let's say that the Earth looks like this. Then you have a source over here. Well, in principle, what you want to do is you want to have a fine mesh to capture the topography. However, it's kind of obvious to us that if the source is here, far away, somewhere around here, this does not really have a strong effect on the signal here. It has effect. I mean, this is a big conductor. This is a mountain in some way. But to discretize, to capture this topography very well, it's an overkill. What you really want a mesh like this. That's what your goal is. The problem is that this is one big mesh point over here and one big cell over here, and they capture now combination of air and other conductivity. So the question is that rises almost immediately, what is the conductivity that I assign with this particular large cell or this particular large cell that contains both air and ground? It's not a trivial thing to tie this to something. So this is actually a very well studied problem in some fields, and you can think about this homogenization problem, an upscaling problem, where you go and you say, there is a conductivity here that changes on the fine scale, and I want to basically put it as one big cell. There is a lot of work on this, and we choose something which is called multiscale methods. Again, I don't have enough time to explain the whole idea, but the idea, the simple or the short explanation is that you can basically solve Maxwell's equations locally. So you can say, I'm just looking at this particular cell, and I'm going to be solving Maxwell's equation only on this cell, with assuming some kind of boundary condition. And then I'm going to generate from this some kind of interpolation matrix that will take into consideration the fact that there is a conductivity here, which is, let's say, close to 1, and this is close to 0, so there is a discontinuity in the solution over here. So this is an idea that we did not invent. We took this idea from people that are working in petroleum engineering. There is a nice book by Tom Howe on this particular thing. And we basically turn it to work for Maxwell's equations. The theory is actually very well studied in other fields. So you can think about this at the end of the day, that you construct some interpolation matrix P, which depends on sigma. It depends on solving many, many, many small localized problems. And you basically construct your coarse mesh operator in the usual Galerkin type approach. Okay. Well, if you remember, I told you before that there is a priori mesh estimates and post priori mesh estimates. I told you that post priori mesh estimates for us is really a no can do, and you can maybe see from here why. If you have one mesh, then you can do a priori mesh estimates. You can look at your mesh. You can say it looks good, it looks bad. You can look at say other methods here. But if you have a million meshes, there is no way you're going to do post priori mesh estimates for them. It's just too much. So we found out that as much as we try, we screw up at some kind of meshes. And whenever we start screwing up the meshes, basically generates an error. But the error is not error in the data. It's error that is generated because of our meshing. It's a systematic error generated because of our meshing. Basically, it's an outlier in the data. So we need to deal with this kind of error. And we found out that one of the ways to deal with these kind of errors, and people that are based in statistics know this thing very well, is replacing the quadratic objective function, or quadratic misfit, which is basically penalizing with a square, by looking at a Huber penalty, which looks like this. And this is an approximation to Huber in some way, that use some kind of like an L2 in the origin and then goes at the end like L1. So this allows you to deal with outliers. So even if we screw up, we have a million meshes, we screw up with one of them or two of them or 10 of them, the fact that we screw up with some of them is not really killing us in the inversion process. Okay, so I want to go back to the optimization problem. Now we say we reduce the size of each linear system. So in practice, you'll see that each linear system that we're solving now maybe have an order of 9,000 variables, so 9,000 degrees of freedom. We can do it with direct methods. We don't have to have iterative methods on this. This is a relatively small scale. But we still have about 10 to the 10 of them. So 10 to the 10 is still very, very large number. And of course, you have to start storing the solutions, and you have to do all these, and to solve them, that really takes too much time and too much memory. So the question is, how do we deal with, how do we decrease the number of forward problems? And the idea is actually, in a sense, straightforward. You can rewrite or write your problem in this way, which is obvious in some way. All you do is you write your objective function as a sum over all the different data that come from different points. You write your gradient of a sum of gradient and the Hessian of a sum of Hessians. So that so far I haven't done anything. The next thing, you can say, if I have a Hessian, why do I need really to take all the different Hessians in order to generate my total Hessian? I can approximate it by just sampling the Hessian, or this part of the Hessian, by some kind of a stochastic sample of the Hessian. So this is an idea that was proposed by Nosodal and Bird recently. Actually 2 papers that they have on this. And the idea that you just go ahead and you say, let's not, I mean, when I do calculation, any kind of optimization algorithm, the Hessian, in principle, all I require is to be positive definite. I don't really care anything else. So you can actually go ahead and sample this, and that's sufficient for convergence. The interesting thing that what they managed to prove, that it will have very similar convergence, just like in the case that you have the whole Hessian. That was the interesting proof in the paper, because again, the fact you can take a stochastic Hessian is obvious. The convergence properties are not so obvious of this thing. Now, when you do this, you already immediately decrease the storage requirements, because when you take the thing that requires you to store all the fields is the fact you need all the Jacobians. But you still, of course, need to do all the forward and adjoint for everything. You just now every conjugate gradient iteration becomes much cheaper. But that's already giving you something. The next thing up the chain is to say, we know if my gradient requires all this sum of everything here, I can go ahead and I can say, well, let's just approximate the gradient here by taking the partial sum of the whole thing. So I don't have to take all the sources and the receivers. I'll just approximate the gradient by taking only a few of them. And there are different types of algorithms about how few you want to take, what exactly you want to do. There is a really difficult book to read by Alexander Shapiro that talk about these kind of things. The idea that you can actually take a few of them is also really common right now in full waveform inversion. For those of you who are looking at seismic problems, this was actually a revolution in full waveform inversion. The guy who thought about this was Jerry Krebs in Exxon. We analyzed this idea later on. Jerry Krebs did not think about it as stochastic programming originally. He thought about it as combining sources and receivers, but it turns out it's a stochastic programming idea. And this thing, if it's done right, you can converge okay, but most of the time the convergence is actually rather slow for this thing. So it depends of which kind of algorithm you do. There is a lot of algorithms here that you can talk about. But again, different things can be worked differently. But again, the amazing thing here, that now at every iteration, if that's all I need, if the number of sources I'm actually using is relatively small, so even if I have 1 million sources, if I'm using only 1,000 of them at every iteration, then all I have to do is compute a solution of a 1,000 forward problem rather than a 1 million forward problem. That's a significant reduction in the cost that I have to do. Okay. So again, there's a lot of issues here. How many samples you need to do? What kind of things you want to do, deterministic or not deterministic? Now, this asynchronous method immediately come here, because if I have to compute, let's go back here. If I have to compute here, let's say 1,000 samples, and each one of them is a forward problem done on a different machine, and let's say that 999 returned to me in 1 minute, but the last one takes it times, and now it's 10 minutes. I'm not going to stay for 9 minutes waiting for this particular one. So how do I combine this information that I got from all of them besides the one that I'm still waiting? It's a question by itself. Again, there are algorithms to deal with this. I'm not going to discuss all these things here, but these are all things that you have to think about when you want to do these things. So these are very important things. The last thing is that if you actually look at the stochastic techniques that exist in the books, you'll find out that they say, for example, you pick up randomly sources from here and you do your thing. But in practice, that really doesn't work very well. And you can see why, for example, when to recover something like this. you have a very small object over here where this is going to be, the data from this will be very localized. So if I'm going to random here, let's say 10 sources every time, I'd be very lucky if I actually sample something above here. I may not sample at all. So one of the things that we actually have done, for example, is change it to importance sampling when we actually decide that we sample more where the data is happening versus sampling in a just a general thing. And you can actually prove some stuff on it looking at approximating integral over a surface. So it's not so difficult to come up with better ideas of how to sample this. And so for example, in this case, we will look at this data and we'll say, well, here we need to sample a bit more. Here we can sample maybe uniformly. And these are things that are really helping in terms of convergence for these kind of things. So there's a lot of work on this, on these stochastic methods. And I find them to be the real revolution in terms of the computational aspect of inverse problems. So once again, if you look at the asynchronous methods, which we're just right now starting to be more or less, we have a few things that are working, but we're still taking baby steps in this. Again, you don't want to wait for machines that are taking too long. And what we're actually looking at a lot of work in machine learning. So machine learning people right now are ahead of us, much more ahead of us, in terms of using asynchronous methods. Usually because they work on data sets that come from the internet, they come at different times, and they need to deal with this. So we're looking at what these guys are doing and trying to learn for this. The things are not exactly all relevant to us because, again, people are looking at information that come all the time, and we're looking at information that exists, and some new things have to be developed. And this is going to be a challenge for us in the next few years. I'm going now to start showing some examples. So the first example is something that people in geophysics actually work pretty hard to put together. So the nice thing about it, it looks relatively geological. So they took a model which is called the Noranda model. So this is a slice in the Y here and X here. And of course, there's a third dimension, which I'll show you later on slices. And it looks geological because geologists were involved in generating this particular example, so it would look real. Because again, if we want to recover some kind of a simple blob in a half space or two blobs, it will be easy. But if you want to recover something that involves large-scale feature, remember this multi-scale structure, there's the large-scale stuff, and then there's going to be all these small-scale stuff. These are things that require, again, to be a bit more careful with what you actually do. And these examples are very good synthetic examples, and it's one of the things that actually, it's another thing that I found in the last few years, at least to my favor, that I think that we need to generate for every field more realistic example to work on. Because if we don't, we can fool ourselves to believe that our method really works well, while if we have a real example or something that's realistic, and we can actually see how it's going to work in practice, or semi-practice. It's not exactly practice yet. So there is a lot of details here. I'm not going to tell you all about it, but we're imitating a system which is called a VTEM system. This is a real system that is being flown. It's by a company in Canada. They fly, I'm sure they're flying right now. I think they have like 10 planes, and I'm sure they're flying as we speak in a few places in the world. So this is one of the things we have. We wanted to do something relatively simple and relatively small, so we actually took only 1,000 meshes or 1,000 sources, because we wanted to play with this. We want to have something that comes to us in an hour, not something that comes to us in 2 days, and to see how different things behave. Okay. So here is how different things behave. This is the true thing. So you have your survey around here. This is a slice in the XZ direction. This is the recovery that you get. We're using all the information. So we want to compare what happened when you do all the information versus all the stochastic techniques. And remember, using all the information is impossible when you're actually doing it on a real thing. So this is all the information. This is the stochastic gradient approach. And you can see that the results are rather comparable. Maybe there's a few things here that you discovered maybe a bit less. So there was this layer here that it's not so visible in other things, but the results are actually pretty reasonable in everything that you would have here. You can do these recoveries and you get reasonable results for this. We looked at what happened locally when you do these. So again, the global features is okay, but what happened to the local features? So the local features, which you can see here, again, it's sliced in the X, Y, and then the XZ. You can see that this is the thing here. This is what you do it. That's what happened when you do importance sampling. And again, if you don't do importance sampling, then you're losing it. So without importance sampling of the data, things are completely lost. And that's something which we haven't seen anywhere else. So this is new, at least and we're right now writing the paper on these random methods that actually require importance sampling. This is the typical things we want to see. So one of the advantages of using some kind of a penalized least square or regularized least square is that you can actually look at the misfit and you see that you're doing some progress. And of course, you see that you are converging. So you have the red curve, which is a stochastic one. You have the blue curve, which is the deterministic one. And the other red curve here is the different stochastic. So one of them is with this is with the Hessian, and this one is without the Hessian. And you don't get exactly to the same misfit, but it's a bit difficult to compare because you're minimizing something slightly different. Okay. Last example I think that I have here is actually an example with a real data set. This was actually done by Elliot Holtham, who is working for a company called Computational Geoscience using our code. This particular thing, there's a lot of geological words here that I don't really know, but you can read it. And this is done basically in northern British Columbia. There is a bunch of properties that, as much as I remember, BP or I think BP are have in charge. And what they want to do is they want to recover the water tables. They want to see basically the water table under these particular things. So they fly these things, and again, this is a SkyTime system, so this is the same system I show you actually flying. This is the Norwegian system. Here you have 2,400 line kilometers, so you can think about in spaces of 50 meters, so you can think how large these things are. Sorry, 200 line meters spacing. And it's not very conductive, and the cell size we're using, the smallest cell size is going to be 15 by 15 by 7.5, so that's more or less what the resolution that actually people want to see. We get at the end 20 million, or so 12 million cells on this thing for this particular block we're actually inverting. So to show people and to show the industry that doing 3D actually makes sense, we always show them what people have done in 1D, because again, until this year really, people could do it only in 1D, and this is what people would do. And they would look over here, again, they would do a 1D inversion, then we'll go here, do another 1D inversion, then we'll stitch them all together to generate something which looks like an image, right? And you can see all the artifacts of a 1D. I mean, it looks like a 1D at different places. That's what people could do until now. With what we do right now, we get something which can look like this if you basically threshold it to find where the aquifer is. And again, this was done with a company that actually geologists looked at this and said this looks reasonable to them. So you can actually get a 3D distribution that fits the data and looks reasonable. This is in a different block to get, again, the same type of thing. Whenever we actually do an inversion, if somebody doesn't show you this, always ask this. I always say to my students, if somebody does an inversion and don't show you the predicted and the recovered data, don't believe them. So you want to see the observed and you want to see the predicted. You want to see that they somewhat look the same and you manage to kind of recover the main features in the data. If they don't look somewhat the same and there are features that appear here and never appear over here, you have to be suspicious. So you can see that there is a pretty good agreement between these two things. And we believe that we've done a good job in terms of recovering the information in the data. Okay. So 2 minutes short of time, I want to conclude. Again, in terms of the challenge of this problem, is the most challenging problem I've seen in geophysical inversion because of the size and the multi-scale structure of this thing. We're going to reduce the size by using basically multi-scale finite volume methods. We reduce the number of systems by using stochastic programming methods, and we're using asynchronous methods. And right now, we feel we have software that is actually relatively robust. I mean, it's already given to the industry this year. And we looked at basically both synthetic inversion as well as field data inversion. And with that, I'm done.
You were that strongly impressed.
I thought it was that boring.
On the way.
You mentioned subsampling the data stochastically. Did you consider just using some decomposition of the source data map, like a PCA or SVD or the DGM map?
We don't know how to do it. I mean, if you want to do some kind of a source data map, you have to have some kind of way to decompose it. And again, if it's a linear system, you may be able to do this. It's a non-linear system.
Yeah, but just the data. It's a matrix. You can take the PCA of it.
You can do PCA, but how do you model this thing?
Just linear combination of the sources with the weights of the...
That's not clear that this is the one. We looked very strongly at combination of data. I actually started from combination of data because that's a seismic problem when you combine the data. So the trick is this: if all the data share, if all the sources share the same receivers, you can do this very easily.
Yeah, sure.
If the sources don't share the same receivers, or if the standard deviations are not uniform, even if they all share the same receiver, the minute the standard deviations are not uniform, you're gone. There's no way to do this, at least not in a direct way. You can show that if there is a low...
No, that's not the case. I can do that.
For standard deviation, which is different, I think you'll find it difficult. I looked it up.
But I'll show you how.
Okay, I'll be happy to learn.
Do you use the same subsampling of data of sources for different iterations, or do you change according to it?
So I said there's a bunch of different algorithms. My favorite one is to change only at the end. We argue about this, not only we, there are arguments about this right now in many conferences. Personally, I like to change it at the end. A lot of people right now claim you should change it at every iteration that gives you better results. The reason I like to change it at the end, because if you change it at the end, you can use, so you do one, you basically iterate to the end, then you choose another subsample and iterate to the end, and you choose another one and iterate. And the reason I prefer it like this, because when you actually change it every iteration, you're very limited in terms of algorithmic selection you can use. Basically, you have to have some kind of either steepest descent or something which kind of looks like a steepest descent with some decay parameter. Convergence is usually horrible on these things, unless your problem is very, very nice. And our problems are not so nice. So on the other hand, if you fix the subset, you are basically free now to use any method you want. You want to use a complete Newton method, use a complete Newton method. But there are arguments about this. So it's if you look, one of them is called basically stochastic sampling, and one is semi-stochastic sampling. So you depend which variant you want to work. But these are different methods in some way.
Is your multi-scale finite volume method designed for the DC resistivity equation or for Maxwell equation?
We designed it for Maxwell's equation particularly, but we looked, I mean, the way we learned how to do this, we started by looking at basically the DC resistivity equation. So actually, they don't call it DC resistivity, this is the groundwater hydrology, correct? So these guys are saying that this is for the pressure equation, but it's the same equation. It's all div sigma grad, and there you have a basis function if you want to look at the details that is nodal. And basically, so you get one of the nodes and linearly decaying in Maxwell's equation, because the natural basis function is going to be constant at the edge and then linearly decaying. You have to change the basis function, and then you come up with the same idea.
What are the boundary conditions?
So the boundary condition of this thing are the Richlet boundary condition when it's, let's chalk here. In the 2D case, it's easy to plot. So there are 4 basis functions in the 2D case, although we never did a 2D case. You put a 1 over here, and they're linearly decaying to 0 here. That's the natural basis function. It'll be the same, the same family as what people do for the stochastic finite volume when they have nodal gradients, correct? So there's nodal functions. Then they do some one here and linearly decaying, and if you take the gradient of this thing, because that's the natural thing to do, you get exactly the basis function we did. So that's kind of corresponding to looking at Nedelec elements for the Maxwell, and looking at basically the H1 elements for the usual nodal elements.
In terms of your grid, you're saying that you're using adaptive gridding. Is that only, are you actually only designing the meshes once based on the a priori information, or you're actually doing some adaptation?
So again, it's a priori, not post priori. So the adaptation is only done before, and in a sense, I know where my source is. I know what my Green's function looks like, so I know the decay of the Green's function, and I'm using only that in order to design my mesh. I'm not doing a post priori estimate, which is the more classical way to do it. Probably the more give you better results. Not probably, we know it gives you better results. But again, if you have, the problem is if I give you 100,000 meshes to design like this, that become very hairy. So after looking at this, we decided we're not going to look at post priori estimates, only on a priori estimates. And you try to be as conservative as you can, because you know that you're going to screw up some of the times, correct? I mean, if I do a priori estimates, but because all the things you have, all the Green's function you have is going to be for a free space or for a half space or something relatively simple. You don't really have the Green's function for a mountain, correct? So you are basically coming up with a Green's function that sometimes you screw it up, and therefore you have to have a mechanism to say, well, it could be that my mesh is not exactly right. Basically, it's a mesh that takes care of outliers that are generated not because of the data, but because of your mesh. which is usually we think about it, the data is bad, our modeling is good. This time I think the data is good, my modeling can be bad.